Okay, so thanks for inviting me to this EUCP session. I'm going to talk about the UK climate land projections. So these were published in 2018 and are the UK government's national official national projections. And I'm going to talk about progress towards more information on future weather. I'd like to thank all the authors there helped with the UKCP, except for Joe at the bottom, who comes in later in the talk. So after an overview, I'm going to talk about global projections. So these are a couple model runs done at a resolution of a seasonal forecast model, and therefore better representation of the circulation, climate variability and extremes. And that's what my team did. And then I'm going to use two examples to illustrate one, first of all, how they might put, say, future weather in the context of topical weather that's just happened, or by linking to other tools, say, such as the seasonal forecast, and some of the issues that might surround that. So UKCP18 actually had 6 products. That's way more than it had in 2009, its predecessor. And 3 of these are the land projections, which are the ones, can you see the cursor there? Moving around, top right. Anyway, a lot of these projections were, products were developed, driven by new science, such as this, the new kind of coupled model we got, but also developed with users. And a key philosophy was to provide more information on future weather and open up new ways to support decision making and communicate the projections. So the first land product was the probabilistic projections. Now, we wanted to move away from the 30-year averages at UKCP09, which were quite difficult to communicate. And so we've moved to seasonal means for individual years, and that really helps. We've also included more CMIP5 information, so they're up to date. And these are basically used for risk assessment, but they're also used for putting the other 2 products into context. So the 2 other products are these regional projections and also the global projections. And they're both spatially, temporally, physically coherent raw model data, which means they're great for, they're flexible to use, they're great for a wide range of applications, and you can use several variables. And the regional projections are 2 flavors, 12 kilometer and a 2.2 kilometer convection permitting model. They just use the Met Office model, the regional projections, and they're for the RCP 8.5 scenario. And they're driven by Met Office global runs. So we've run 15 perturbed parameter coupled model runs at this seasonal forecasting resolution of 60 kilometers in a quarter degree ocean. And then 12 of those were used to downscale the regional projections. And then the 15 were kept at the global projections, and they were augmented by the 13 CMIP5 models. And this is a kind of example on the right-hand side here of what they look like. So this is about putting the projections, the global projections, which are the orange and blue lines, and also there's a red line, which is an example of one of our perturbed members. And for winter precipitation, we put it in context of the probabilities. So this, the grey shading shows you the evolution of the sort of 5th and 95th percentiles. And you can see there's quite a good comparison in this example. You can see the black line here is the observations, and the variability actually of the projections is pretty good. It's not too bad. What we've done though is moved away from a message which was all about winters are going to get wetter, to now we can say we're still going to get some dry winters, but wet winters are going to become wetter, and that's a subtly more informative message. So when we designed this perturbed parameter ensemble of coupled runs, we had 2 concepts in mind. One was plausibility and one was diversity. So we're trying to get plausible models, but they're diverse in their kind of climate response. And to do that, it's very difficult to explore parameter space and achieve this. So we had to resort to using cheap models to do it, so atmosphere-only AMIP type runs. And the first set at the present day runs were used to filter out poor performance, get rid of some parameter combinations. And then the remaining set of parameter combinations we used further AMIP runs, but with an idealized 4K warmer SST pattern to kind of make sure that we sampled, as well as possible, a range of climate responses associated with that warmer SST. And when we looked at the plausibility, we actually did pretty well. So the top left plot shows you an example of the root mean square errors for the different seasons for the storm track density, and the orange dots are the coupled PPE, and they do very well in comparison with, say, the CMIP5 examples. What was a bit more of a surprise was when we looked at actually the response, and we looked at this plot here of the global temperature change. And as you can see, there's the CMIP5 ensemble here, the blue spread, and then all the 15 model runs were from the Met Office were actually all to the top end of that, or if not above. And there's 2 reasons for that. The first is actually that we, in these runs, also sample CO2 uncertainty. So we have 15 different emission pathways, all consistent with the concentration pathways, all consistent with RCP 8.5 emissions. And it turns out that 80% of those are actually higher than the CO2 in the standard RCP 8.5 concentration that CMIT5 used. And then the other reason was that the model that we perturbed is structurally predisposed to having a higher climate sensitivity. And so in the end, these 15 runs explore a range of about 4 to 6.2 Kelvin. So that's the two reasons they're warmer. And in some ways that's good, because the PPE is actually exploring a high-end warming that the CMIT5 couldn't explore. But and the good thing is, about having both of them together, is that you explore the greatest range of uncertainty that way. When you look at the regional level, there's actually more overlap, but that's partly because there's more spread maybe, but there's also more spread, and internal variability is greater in the Met Office model runs. In all, though, the CMIT5 model runs do a better job of sampling the long-term averages and the response there. So we have to do some work to do a better job there, I think, with the parameters. And I'd just like to point out that Carol McSweeney's poster on evaluation of large-scale circulation is relevant to this slide and looks really good from what I've seen. Okay, so the second half of the talk now is to give two examples of how we can progress using this new capability to communicate projections better. So by going to one-year averages, we've already helped the probabilities being used for communication. For example, the probabilities can now give you the probability of, say, what happens when you observe a summer, say the 2018 one, which had a big heat wave in the UK, and that's about 15% from memory. But there's also work that can be done, and work in social sciences has shown that actually qualitative information in the form of stories can help users understand the risk. And if you can present that information in more in terms of things they understand, like, and can relate to, like weather, seasonal averages, then they suggest that the uptake of the projections is likelier. So here's two examples, just a flavour of what we can do. We've done more stuff, but I'm trying to make 2 points for this. So this example is about getting topical weather and putting the future projections in context of that topical weather. So last year, 26th of February 2019, we had the UK experienced its hottest day ever, and Kew broke the record, 21.2 degrees C, which was 1.5 degrees greater than the 1998 previous record. And what we decided to do was look at our 28 projections and try and mimic the way the Met Office had presented the numbers and the way the BBC were reporting them, which was so what we've done here, and I'll show you on this right-hand side, I'm going to zoom in on 4 of them. So you have 4 of the Met Office models at the top and 4 of CMIT5 at the bottom. And what we've done is we've taken the hottest temperature, daily maximum temperature from any of the 64 UK grid boxes in any of the winter days, and we've done that for each winter and then plotted the time series. And I think the first thing that strikes you is actually the hottest days in some of these runs really stand out from maybe the 3rd or 4th hottest. There's a big gap. So this grey line here is the historical period, and for each of these runs, we haven't bothered about bias correction or anything like that. We've just let it define its own record, and that's the dotted line. And you can see that generally there's some outliers, but also there are numbers like 15 and 22 here where there's less outliers, and you see that actually most of the maximums are close to the record anyway. So that has 2 consequences. The first is that actually, when you look at when the records were broken across the 28 members, they can actually be broken any time during 1900 to 2020, and that suggests that internal variability plays a massive role. But also you get more records towards the end, and that's just anthropogenic warming can top it up a little bit. And then to put this future weather into context of the topical weather, we looked at how many days in the future might break the historical record. And then for each number of days, we'd count the number of members where that happened. And you can see that actually there is a chance of occasionally breaking the record, like 1 or 2 days in the season, but it's not until the end of the second half of the 21st century where it actually kicks in. And bear in mind, these are really high warming scenarios. So these records that have happened are really quite strong if the kind of models are good at this. So hopefully that when weather happens, the idea is when weather happens, then we can sort of report on this kind of thing. So we can report on future projections when it's fresh in people's minds. The second one is an example on tropical cyclone landfall in East China. So this is part from the China project. And this is based on work that Joe Camper's done, which he uses the seasonal forecast to look at, she's interested in how much landfall you get over East China. And she looks at something called the West Pacific subtropical high. So in this top right plot, what happens is if this high is enhanced, it stretches right over and it pushes all the tropical cyclones, a lot of them over towards southeast China. On the bottom, if you get a weakened one, then you get more cyclones bending around and they can hit East China. So I wanted to look at this and give it a future context. So the thing was that actually, when she does geopotential height over this box, if you look at that in a climate change experiment, it just like goes up because it's got a large thermodynamic component and it kind of picks up the global warming. So we've looked at other indicators, maybe ones where you remove the zonal mean first, which Huang et al. Did, or Huang et al.'s other index where you look at the western extent of the zeroth line of that kind of eddy geopotential height. And you can see then maybe you're getting more at the dynamical driver. So this is one of the issues. If we're going to go across timescales, we have to find indicators that are relevant to all the timescales. And just down the bottom here, see 000 is pushing towards more tropical cyclone landfall, whereas these other two runs at the bottom are pushing towards less. So in summary, the climate models are improving a representation of the circulation and variability, and users are interested in a range of timescales from seasonal to longer term. So if we can run a couple models, explore uncertainties at resolutions to seasonal forecasting, it's opened up new opportunities for us to present and communicate the risk of climate change. But there's work to be done on trying to make those, crossing those timescales. And the other thing I'd like to point out is that there's still room for improvement. Find the right balance between plausibility and diversity. And ways to do that might be with the parameter ensembles, more multi-physics kind of approaches like the Japanese, or different ways of filtering. That's it.